Okay, so which I'm just gonna go through the spec then that's give us from the start.
Okay.
I'll share my screen now. Okay, so well, the whole point of this booklet was to build a security system for the sky. Although I don't think we ever do that technically, but anyways. So main concept here is electricity versus electronics. Now, most of you guys would use this term interchangeably, meaning you use one or another for the same thing, right? However, the difference is with electricity, we mainly deal with high voltage. So that would be plus 230 volts. Anything higher than from 230 and upwards is considered electricity because, and when we deal with electricity, it's mainly AC because, and how electricity gets to your house. With electronics, we're looking at your appliances, how your circuits work. And so mainly this is DC and the lower voltages, for example, 5 volts to like around maybe like 100 volts, right? Obviously with exceptions. And this, so electricity, we look at how electricity is transported to your homes and the power pylons. However, electronics, we look at the circuits that we build. Okay. Um, Obviously your basic circuit diagrams, and that's the main difference. So obviously your various power sources, you look at like ESCOM, solar. Now, key thing to note here is power source. You don't say, even though it says batteries here, a battery is not a power source. A power source, for example, ESCOM is a power source. They provide power. A battery, although yes, it does provide power, still needs an external source. For example, you need to charge it with electricity still. So just keep that in mind for that. So any device that uses electrical energy is known as an electrical system. Now, what an electrical system does is it takes your electricity and it converts it to heat, light, sound, or movement. Now, obviously, it's dependent on the circuit what it does, but most of the time, any circuit will produce a small amount of heat. Okay, so um, so the difference when we look, so many of these circuits have something called a sensor. Moving forward from here, now sensor is your input. For example, when you look at that, we say so the this is an electrical system. And with sensor, there's three things, right? So first of all, you need a sensor, some way to process it, and how does it respond to that. Now, skipping forward, that's input, processing, output, and feedback. So your sensor would be your input, your process is, for example, what does the circuit do with this information? For example, let's say you have a switch. When you flick that switch on, what does the circuit do with that? Obviously, that conductor now. Then from there, you get the output. And that's your output. And your output obviously takes that data and it converts it to one of these here. Now, I know there's a fourth one, which is the feedback. Now, the thing is, I'm gonna be honest with you. This booklet has a lot of mistakes in it. As some of you can tell, I've attempted to remedy these errors in class. However, thing to note is feedback is the same as the output. Feedback, sure, whatever, it gives you feedback on the circuit. For example, a voltmeter, that's also an output. A voltmeter is still an output. So I could argue with sir, and I have, but he said no, that it's still feedback. So just keep feedback there. Now, um, in this case, let's take a simple cir- if you take a simple circuit that yes, it will be posted. Okay. So if you take a simple circuit, like for example, it just has a light bulb, a switch, and a battery. Then it's simple to identify. This is your output, this is your input, and this is also an input because it inputs energy. So that's when we get into the classification of each set, of each component. But before we do that, all four of these things work together to form the electrical system. However, yeah, whatever, it can be assembled and interconnected. Okay. Then the input. So moving on, the input. Now the input is it's in the name input. When you look at input, you look at a power source, or you look at something that does logic. For example, a switch. Now we'll get back to this keyword here, logic. Now, power. Power can be your normal cell. Now, cell meaning one. This is a cell, and this is your positive terminal. The longer one is your positive terminal, and the shorter one is your negative terminal. A battery consists of many of these cells. This is just the simple stuff I'm going through. It does the exact same thing as a cell, except it's multiple. Now, you look at an LDR. Now, we just wrote robotics last week, so this should still be easy for you guys. Now, I've asked her, and you see those symbols we have in the pack. He said, I showed him our symbols, and he said it's fine, we can use either or. Now, because of what my preference, I'm just gonna do both of them for you, but you can decide because I prefer using the standardized ones in robotics from robotics. But this is the one way, and the other way is this here. So you just decide which one you want to use. And if sir does not give you a mark tomorrow, don't worry. I will make sure that you do get your mark if you draw either or. Then it's that's simple. It detects light energy.
We don't get our
What's wrong?
our papers
I, ca-
back.
I
We
can't
don't.
hear you. Okay, then. Do you have a question, Josh? We don't get our papers back. Oh, that's weird, but okay, anyways. Nothing I can do. Just use the symbols there, the set of symbols there in this case. So don't worry about this. Okay, LDR symbol. It measures light. The more light you have, the less resistance. The less light you have, the greater the resistance. It works based on photons. So that's simple stuff. Then next you got a thermometer, whatever, a thermistor or something like that. Whatever, however you say this. It detects changes in temperature, and the symbol is this here. Changes resistance. Now, in a well, both of all of these are sensors. These two are both resistance-based sensors, right? A thermometer is based on temperature, and then LDR is based on light. Both of them vary in resistance based on environmental factors rather. Okay, then next, you get a push switch symbol. You open or close the circuit. Hold up. Okay, you open or close the circuit. Push switch, you have to hold it. Okay, don't worry. It's simple, opens or closes the circuit. Then you got a magnetic or a reed switch. Now, this is a new one that we've done that isn't in robotics. And the symbol is this here. Now, when you place a magnet next to it, the switch will close. So this is a magnetic based logic. It's based on a magnet. Then got the vibration switch. It takes changes in movement. It's quite simple. With the lines here to show vibration. Oh yes, I forgot something. So this is a normal switch. You get a push switch, which you have to hold down. So regarding the symbols, most of the symbols are based on the physical components if you tear it apart. Then after that, after you get a moisture sensor, which now if you remember correctly how a moisture sensor looks, the water will bridge a gap. So if you ever forget the symbols, most of the time it's based on the physical component. So when it detects water, the circuit is complete. Light depend. I don't know why there's a second LDR, but anyways, okay, that's all your inputs. This is all under inputs. Then you get some. Okay, yeah.
Josh has a question.
Who has a question, Josh? Is sir gonna tell us to throw the symbols? I would not know. Okay, I don't know. So it's like he just said this whole pack. That's all he said to us. But it's not so. But it's easy to remember. It's not that bad. It's not that many symbols. Okay, next is the process. Okay. Now the input it does something. It provides data to the circuit, makes the circuit turn on and off, provides power. For example, the on and off switch on your light. That's part of the input. You inputting energy to make it do something. Turns it on. on or off, right? Now, the process is what the circuit does with that data. Now, this, so the processor, think of it as the brain. It's the brain of the circuit. Because, uh, for example, when you turn your volume knob on your speaker, how does the speaker physically get louder? The circuit provides more power because of a potentiometer. Okay. Um. Anyways, so processor is the brains. To make it, think of it as the middleman between the output and the input. Takes this data and turns it into other data that the circuit does something with. So you get a transistor. Our symbols slightly more complex with an arrow here. That's B, C, and E. Now in a transistor, what it is when you apply current here, the gap in between these two is bridged and the circuit flows. Meaning instead of requiring a switch, you instead of having a switch, you have a transistor. In your phone, you have about 6 billion of these in your processor alone. 6 billion of these small things that does logic for you. Now, transistor is useful for, so let's say you have a geyser that you need to turn on and off. Now, the switch required to handle the current for the geyser is larger than what you have. It's larger, the physical conductor is larger. Now you need some way to turn it on. What it does is it uses a transistor to use a smaller switch, and you hook that up to the transistor, and it allows current to flow. For example, in a speaker, the on and off switch is hooked up to a transistor, which allows for current to flow instead. Then you get a resistor, and the resistor we've been drilled, well, since when it is just a plain block box, I don't know. And the resistor limits current in the flow in the circuit. I don't think I need to explain resistor. Then next is the capacitor. Now a capacitor is also new to you guys. What a capacitor does is it stores current, right? Now where it's basically a small battery. Think of it as a small battery. Now in a motor, okay, wait, let me use a better example rather. A capacitor stores a small amount of electricity and then you can use that. Now, it's used in is timer circuits. So, when you want to set a timer, you add a capacitor and it allows you to control the duration of something before the capacitor obviously runs out of energy and the circuit breaks or opens. Diode, quite simple, same symbol. Now, the diode allows electricity to flow in one direction and blocks flow in the opposite direction, used as a form of protection, surge protector circuits, simple stuff. Now, for some reason, I don't know why this is in under process, but you got a variable resistor known as a potentiometer. This should definitely be under input along with the resist. But yeah, it is what it is. I'm not the one who made this pack, but manually increase or decrease resistance, meaning it's another form of a variable resistor like these two here. Now, the thing with the potentiometer, it's used in your volume knobs that you physically turn, and then a variation of the potentiometer is known as a preset potentiometer, where You set it once and you leave it like that. So inside specific electrical devices, you may find this. Now that's all the input. That's all the process. Now, moving on, we got the output. Now the output is what the circuit does. Yes. Yeah.
Isn't do we have robotics tomorrow?
Now we had robotics today.
But Ravi, can you like maybe answer for us if we use the symbols that we had in robotics, if it will be correct or answer?
Yeah, I'll ask her tomorrow in Hello. Because
Okay,
I have my booklet with me. And I'll just show him again just to remind him.
okay,
Okay, but just
okay.
let me know which one you. I'm gonna ask him if we can use either or because then it's easier on you guys. Because then you only have to
Yeah,
learn one set and you can choose which set.
okay.
Because the ones in robotics are standardized compared to this here. Because drawing a block in 90% of electronics, that means nothing. But it's technology, so it's special. But I'll ask them. Anyways, the output produces, it takes the information from the process and it does something with it, something useful. Now, now it's the output energy specifically. It outputs energy. Now, you get simple. For example, in the radio, speaker generates the sound vibrations, and that's how you're listening to me right now while I'm talking. Now, in a mode, you get a motor, which when you connect it, spins, simple stuff. A buzzer, which when connected, produces sound energy and it's used for warning alarms. An LED, which I think we all know by now, this one has a circle around it though. An LED used in as an indicator light, a loudspeaker, which is used in your generally your larger speakers, and a light bulb, a normal light bulb to produce light. That's the output. Now, these three things form part of the electrical system. Now, feedback ensures that the process section is functioning as intended and generally does use outputs to determine this, for example, LEDs. Okay, moving on, what is electricity? Okay, now electricity flows through a conductor. The electrons flow through a conductor. Now, that is electricity. For example, a wire carrying the energy from the battery to a lamp, for example. Now, there has to be a complete circuit. Any breaks in the circuit means that the electrons cannot flow correctly. Now, it has to be wired in the correct way because if you switch something called polarity, what this means is if I have a cell here, I connect a diode. If I connect this is connected wrong because this is the negative side, this is the positive side. Electricity will not flow in this case, but that you don't have to go too in depth. Now, for electricity to flow, there must be a complete enclosed circuit, allowing electricity to travel from the positive to the negative terminal of the power source to interact with the components and return to the negative terminal source. Now, there's two different types of current directions: conventional and electron, E and C. What this means is that when first electricity So any electrician uses something called conventional current, which flows from positive to negative. Quite simple. However, electrons are negatively charged, and we know that electrons will always flow from it flows from a negatively charged item to a positively charged thing. That means that this is conventional, and in electron flow, the flow of electrons is the opposite. They flow less from negative to positive. The reason being electrons are negatively charged, and that's why we get. So generally, in electric, when if you've met an electrician, they use conventional current. Scientists use electron flow, and then that's the main differences. Because so obviously at the time, scientists couldn't determine which way electricity flows. Many tests were done. They made essentially it was a guess, and that's how we got conventional current because it's a guess. However, when the electron was discovered that it had a negative charge, that's when they created electron flow. Because electron flow is the well, electron flow is in the name. It follows the electrons. Now, beginners use conventional, and most people use conventional. However, scientists would use electron because it's more accurate in determining diagrams. Um, okay, so that's the main differences between those two. Then, next, we got voltage and current. Now, current refers, current is how quick the thing flows. How fast electricity flows. So when you measure current, you're measuring how quickly the electricity flows through the circuit. Voltage is how strong of a push it has. Now, voltage, let's say voltage is the strength of the current. Now, based on what I've told you, this is just a question to see how well you understand this. It won't be assessed on. Which one kills? If I have a high voltage or if I have a high current?
High voltage.
Does anyone know? So let's say I touch a high voltage plug but a low current plug compared to if I touch a high current plug
High
and a low
voltage, high
voltage
voltage,
plug.
high
What
voltage, high
happens?
voltage,
Which
high
one will kill
voltage,
me?
high voltage,
Voltage or current?
voltage.
Voltage. Is it voltage?
I don't think you can hear us, Isaiah.
Yeah.
Hold up, I'm just gonna try. Something's wrong with my audio. Just wait.
Yeah, Isaiah. Told you, Isaiah. So I got it first, Isaiah. I got it first.
I know. I just copy what you said.
I just think like if you touch
I haven't
a
been
very
paying attention.
oh no, Isaiah. You need to focus. Isaiah, I have a blister today.
I'm what?
I want
I'm trying.
right today. Yeah, bruh. Done.
Okay. Did that fix everything? Let's see. Is that better? Can you hear me now?
Isaiah, you must mark Johnny, bro. Yo, I had a test difficult to mark, yo.
So he's annoying. He just grabs you. He steps on you.
And it hurts, eh? It hurts.
Nothing you can do. He gets past you once everyone says he cooks you.
Ah, that makes me mad. Yo.
They
Okay,
flatten your issue.
Ooh, John,
Okay, too.
yo, fake crust.
They setting
hello.
down.
Can you hear me? Okay.
He's like, yeah, my friend, that guy Tiamo, we have Katisho Mbappe.
During the game.
He's not sitting nobody down.
I'm
Can
not
you hear
sure.
me?
And I have
Okay.
faith in
Now.
Chuck. I have faith in Katisha.
Okay, can you hear me now? Is that better?
Yeah.
Can you ask Pravia?
Yeah, I can hear you now. That's better.
Pravia, voltage, Pravia. Don't let
Okay.
us
I
get
said
ready.
I said it first, by the way.
It does.
What?
Okay. Can you tell me why?
Because high voltage is what comes out of the battery. And like voltage is high, bro. Trust.
Okay. You got the correct answer, but you don't understand why. Let me explain
Yeah.
quickly. So the straight. So let's say I'm running quickly. Okay. It doesn't matter. Okay, like let's just exclude normal physics, right? If I run into a wall, it doesn't matter how quickly I'm running at the wall. I will come to a dead stop, right? Okay, just a hypothetical question in a perfect environment. I will come to a
Yeah,
dead
yeah,
stop,
yeah.
right? But now let's say instead of moving a slow bulldozer against the wall, bulldozer is gonna plow through the wall. That's because in this case strength will kill you. Because it doesn't matter how quickly the electrons are flowing through your body. It matters how strong it matters how strong the current, well, how strong the voltage is. That's why voltage kills. So when you're working with circuits, be careful because higher voltages will kill you. Current doesn't really matter. That's just how quick the voltage will reach you. Okay,
Okay.
moving on. Um, so these two things are always measured across 2 points in a circuit. Um, right. So you've done diffusion, so you know it goes from a higher concentration to a lower concentration. So this is a high concentration and this is a lower concentration. So electricity goes in this way in this case. We're just using conventional current. Now there's two types. Two types, AC and DC. Now, the way I like to explain it is AC switches. AC is a confused person. Doesn't it doesn't know what it wants. Because they so if you look at AC, it's your high voltage, your higher voltage.
Yeah, Pravia, you said AC is a what?
So AC is the confused person. Doesn't know what it wants out of life.
Oh,
Because one let's say I measure it, right? My positive is this side here on this terminal here, and my negative is on this terminal here. Then the next second you know they switch. They go back and forth.
oh, okay. Thank you, thank you,
They
thank you.
basically switch around, right? Now This is that's why it's higher. What allows AC to be higher voltage because it's more efficient at transporting higher voltages of electricity over a distance because it has the ability to switch. Okay. Then you look at DC. DC is your low voltage. Now, simple. Your positive is always positive. Your negative is always negative. DC. Your phones and that run on DC. Any electrical circuit, for example, inside your appliance, if you take it apart, most of the time you get it converting it from from AC to DC, and then it uses DC from there. So, for example, your laptops, your charger converts AC to DC to charge your battery. Now, yeah, it's used to power batteries. Then circuit diagrams. Now, circuit diagrams, it's going to be a bit difficult. Well, it's not difficult in a sense. It's just that I'm going to have to draw them now, properly. Okay, anyways. Now, there's two ways that 90% of the time no one draws the physical circuit, the physical light bulb out on the stand because that's slow. So we use symbols instead. Now, obviously, that's where the symbols from earlier come into play.
Ravi,
Yeah.
didn't Sir say like in the booklet like he can tell us to draw the diagram where we have to like draw actual light bulbs?
Is that
Like he
anywhere
said,
in this booklet?
yeah, it says circuit and in the circuit diagram. Didn't Sir say he can give us the circuit diagram and we have to draw the circuit?
Yeah, I don't know. But anyways, like circuit, like why would we want to draw the circuit? That doesn't make any sense. But in that case, you must just know how to draw because it won't be two hectic circuits. Okay, right. Circuit diagram is easier to use, so it's used more commonly, but in this case, we're gonna have to use this now. Right. Now, series and parallel versus parallel. Right. Now, series is simple. You see one path of electricity. Electricity only flows in one path. Where it's used, for example, your simple circuits like your one LED or and a battery and a switch, that's a series circuit. Now, your house is not wired in series because if anything breaks there in the series circuit, everything will go off. So if anything is broken, the whole circuit is off. However, that's why we will wire stuff in parallel instead. Parallel gives us the advantage of, okay, I have two light bulbs. If one is gone, the other one will still work because the electricity flow is not disrupted. So your Christmas lights and that are wired in series because it's easier to have them like that. Then your main lighting, if you look, your ceiling and that is wired in parallel because you see if one globe goes out 90% of the time, all of them are fine. The rest are fine. That's that's series and parallel circuits. Then conductors and insulators. Quite simple thing. Now, a conductor obviously is good at conducting electricity. Insulator resists current. So, resistance. Every material has resistance. No matter how good of a conductor is, it has resistance. However, 90% of the time that resistance is negligible. In copper wire, resistance is almost negligible at a small length. Um, this is just saying, like, for example, glass and plastics have a high resistance, and okay, that's it. And then copper, for example, is a good resistor. Electrical components, we went through this, we went through a resistor. Now, thankfully, here we have a simplified table Sir gave us. It's only the only difference between this table and the robotics table is the robotics table has all the tolerance. The Sony S3 being red, which is 2%, gold, which is 5%, and silver, which is 10%. Now, do you guys want me to go over how you identify this? How to do your resistor color coding and that, or can I just skip over it and carry on? Okay, I'm gonna say we'll carry on going. LDR convert light to resistance because it's based on we went over that transistors. So they're used in switch. It's a digital switch. I explained that to you. LED we explained. Um, Now Key thing to note with an LED is it always needs to be wired with a resistor because the current is too large in many circuits. For example, if you use a 9-volt battery, you need a 1000 ohm resistor to protect it because the current flows too fast in an LED for an LED to handle it. Okay. Buzzer convert electrical energy to uh, obviously sound energy. The more voltage is supplied, the harder the buzz, and it must be connected the right way around. The red LED is positive. Now you get types of switches. I've went over the simple switch, the push switch, reed switch, and loud. I don't see why a loudspeaker is there, but anyways, when you bring a magnet close to a reed switch, it completes the circuit, right? Now, circuit diagrams. Do you guys want me to go over, or are we good? Just raise your hand if you want me to go over that. Okay. Lamps in series. Right. This is where you have to be careful because in series we look at resistance easily, right? Resistance is quite easy in series because you just add them up. Your resistance total is equal to R1 plus R2 plus R3. Simple stuff. Your current stays the same no matter where you take it from, and your voltage you just add up like the resistors. Simple stuff. Right. Now, parallel circuits, your okay, wait, this is wrong, yeah. This must be an equals to sign. Right. Parallel is similar formulas except you're just adding current. You're adding your amperage. Now, when you're measuring voltage drop in a parallel circuit, okay, let me pull up a diagram. Mm, right. Here's a simple parallel circuit. Now, let's say this is 5 volts. The battery amps doesn't matter in this case. Now, what is the voltage drop across this bulb? Because there's no. So let me explain something. This case, we're only doing simple parallel circuits, so I won't even you worry about that. But in this case, no matter where you measure this voltage, it will be the same. If I measure it here and here, here and here, it's still gonna be 5 volts, no matter what. Because obviously accounting for the small tiny voltage drop, it will still be 5 volts because it's parallel. Now the total current is 10 amps. Okay. If lamp 1 has 4 amps and lamp this is unknown, simple. You're just saying 10 minus 4 gives you 6 amps. Because here, this is series. In a parallel circuit, the current you have to add them up to get the total. Voltage stays the same, and the resistance formula we will not even touch. Logic gates. Now with the logic gates, it's this is a whole nother thing because we introduced to something known as the truth table. Now, you get different gates. Logic gates are used to make decisions in a circuit, meaning we represent on as 1 and off as 0. And that's where you get binary, which is coding programming in ones and zeros. And that's how your phone and computers do it. But however, now with the logic gates, Logic gates take in values and convert it into a different value. For example, you get an OR gate, which takes input A, input B, and it's represented with this symbol here, A and B. A and B are your inputs, Q being your output. Now, we represent it in a table that looks like this here. Right. Now, this is off, this is then off, this is on, this is on, off, on, this is off and on. Oh, wait. That's on, and that's off. Now, an OR gate, let's say input A or input B is on. If either one is on, it will return on. Doesn't matter if both of them are on, it's still on. As you can see here, only if both of them are off will it be off. Simple. Then you get an AND gate, which looks like this here. Flat here, round here, and a Q. Right. Now, looking at it, now an AND gate, basically, both of them have to be on for it to be on. Now, if we're looking at an OR gate, it's simple. Let's say you have two switches connected in parallel in a circuit. Either one will turn them off and on. Doesn't matter if both of them are on, the current will still flow as long as one of them is on minimum. An AND gate, think of two switches wired in series. Both of them have to be on, or else it is off. In this case, only one case is off. Now, this is quite simple because it's in the name. You don't do fancy gates. Because in computers, you get a XOR gate, NOR gate, don't worry about that. Right? Completed. Now, if I gave you a logic gate, would you be able to complete the truth table based on what I've said? Based on what I've said, can you complete a truth table? It will be like an OR gate or an AND gate. Yeah, I'm just going to take that as a yes. I don't have time. Okay, Ohm's law. Do I have to explain Ohm's law to you guys? Because it's Ohm's law. Because really, no. It's Ohm's law. Okay, in that case, then we're done with this whole thing. Because Ohm's law is literally just V is equal to I times R, so on. So I think that's it, gents. If you have any questions, just tell me now or let me know. Okay, I'm going to leave now and upload the video.